Okay, section 2.7 is on solving problems involving more than one triangle, and a lot of times you might have information that you're trying to find, and when you look at the diagram that you have, there's not enough information in the triangle that contains that side or angle that you're looking for, but there is another triangle that's attached to or part of the triangle that we are interested in finding information in, and then we can find information in another triangle to help us find the information in the triangle that we want to use. So a lot of times you look for a common side or a common angle that the triangle shared that will help you move from one triangle to the other. So the first example has two triangles, and you're asked to find the length of x in the diagram. And x, if you notice it, is actually a side from C to B in a triangle that isn't a right triangle. ACB is not a right triangle. And we don't have really much methods that we can use for triangles that aren't right triangles. Most of the methods we have, the Pythagorean theorem and the right triangle trigonometry, are used obviously in right triangles. So if we look, x is actually made up of two sides in two adjoining right triangles. So if we find CD and find D to B, call it Y and W respectively, then we can add those together to get x. So we'll start with the top triangle there. The first triangle, ACD, we have Y would be the opposite and 15.8 would be the adjacent. So we would be using a tan ratio. Tan of 20 degrees is Y over 15.8. And so then we can put that over 1. If we're looking for the side, we usually cross multiply. And we get Y equals 15.8 tan of 20. So we do that on our calculator. We get 5.75. 0729, so on. So that if we round it off to the nearest tenth, that would be 5.8. And then if we calculate the length of W, we can use the bottom right triangle, ADB, and the side W is across from the angle 30, so it would be the opposite side. And again, AD would be the adjacent in that right triangle. So we would begin using tan in the bottom right triangle. Tan of 30 degrees is W over 15.8. And then if we cross multiply, we get W equals 15.8 tan 30. And if we calculate that, we get 9.122, so on. So that would be, to one decimal place, that would be 9.1. So if we put these together, therefore x is 5.8 plus 9.1, which is going to be 14.9 centimeters. Okay, example 2 has a right triangle with another right triangle attached to its hypotenuse, and you're asked to find the values of both x and theta. So if we look at the triangles ABC that contains both side x and angle theta, we don't really have a whole lot of information there apart from the 90-degree angle and the 25.6 side. We don't have two sides, we don't have two angles, we really don't have enough to use any of the trig ratios or Pythagorean theorem. So if we move to the other triangle, ADC, which is attached, we notice that that triangle is attached and it has a common side AC with the first triangle. So we could probably use the information in triangle ADC to help us find side AC, which then we can use in the triangle that we want to use. So I'm going to put, say, W on that side, and I'm going to use triangle. That didn't doesn't look like a triangle. I fix that. I'm going to use triangle ADC, and I would use, here I have 74 degrees, I have the opposite, which is 32.1, and I have the hypotenuse W is what I want. So I can use sine of 74 degrees is the opposite, which is 32.1, over the hypotenuse, which is what I need to find. And then because I'm looking for the side, I set it up so that I can cross multiply. And I get W sine 74 is 32.1. So W is 32.1 divided by the sine of 74. Because you want to isolate the W. So W would equal 32.1 divided by sine 74, and that's going to give you 33.3936 and so on. So that works out to be about, to one decimal place, we'll say 33.4. So then if we move to the other triangle now, triangle ABC, we can actually find the angle theta because we have the adjacent side, 25.6, and we have the hypotenuse. W happens to be the hypotenuse of triangle ABC as well. So we can use cosine of theta is adjacent, which is 25.6, over the hypotenuse, which is W, which we just found to be 33.4. So that would be 33.4. So then the angle would be inverse cos of 25.6 over 33.4, which would equal approximately 39.96 to 3, so on. So that's about 40 degrees. No, it says to round to the nearest decimal. Well, it will be 40 when I round that off to the nearest tenth. And then the last piece of information we need is the length of x. So if we go back, we've got a couple of things now we can use. We can use, we're going to have to use one of the pieces of information we just found. We can either use Pythagorean theorem, because we've got two sides in the right triangle ABC, or we can use trigonometry again with the angle that we just found. So I'm going to use trigonometry, and I'm going to use the angle of 40 that we just found, and x would be opposite, and AB would be adjacent. So I'm going to use the tan of, so this is still triangle ABC. We've got tan of theta, which is 40 degrees, equals opposite, which is x, over adjacent, which would be 25.6. And then if we cross multiply that, we have x equals 25.6 times the tan of 40, which is going to be approximately 21.4809, so on. So that would be to the nearest tenth would be 21.5 centimeters. Okay, example 3 gives you information from a hotel window 100 meters above the street level. So that means this distance from here to here would be 100. David observes a bus moving away from the hotel. The angle of depression of the bus changes from 36 to 20. Determine the distance the bus travels during this change to the nearest meter. So you are looking for the distance between the two spots where David sees the bus. So you're looking for x from here to here. And the angle of depression changes from 36 to 20. So if this is where our line of sight is taken from the hotel window, so we have to draw a horizontal from up there. So we know that the first time he sees it, it's at an angle of 36. And then the second time, it's at an angle of 20. Now, when we use angles of depression, a lot of times we don't want to use the angle as it's drawn. We want to put an angle inside the right triangles. And here we have a little right triangle here from the hotel window to the first bus and then connect there. So if this is 36 using the parallel lines, if this angle here is 36, this one has to be 36 by alternate interior angles. Same thing with 20. If this is 20, you've got the parallel lines from here, up here, and the road. So this angle and this angle would be alternate interior angles. So they would be equal. So then we can use that in the bigger right triangle, which goes from the hotel window down into the bus. So then we've got two right triangles that we can use. So in the smaller right triangle, I don't have a whole lot of room here, so in the first right triangle, if we call this A and this B and this C, we can actually find this distance right here, B to C, by using the tan ratio. So the tan of 36 degrees would be the opposite, which is the 100 over the adjacent, which would be y. And when we put that over 1 and cross multiply, we get y times tan of 36, sorry. Y tan 36 equals 100. So therefore y would equal 100 divided by tan of 36, which is 137.638. So I'm just going to round that to 137.6. And that would be in meters. And then we would look at the bigger right triangle. So in triangle A, B, D, we have, again, we can use the tan ratio. We can use the tan of 20 degrees is opposite, which is going to be 100, because this is the triangle we're using now from here to here, here. So this would be 100 over, and I'm just going to call it, from B to D, I'm going to call that W for now. So that would be over W. So just kind of see if I can squeeze that in down here. So then that would put this over 1, and we cross multiply. And we're going to get W tan 20 equals 100. So then if we want to get W by itself, we're going to have to divide both sides by tan 20. So W would be left on the left side by itself, and we'd have 100 divided by tan 20 on the right side. So 100 divided by tan 20 will be 274.7 meters. So now if we take the W and subtract the Y, we will get the distance X. So therefore, 274.7 subtract the 137.6 will give us 1,000 works out to be 137.1 meters. Yeah, the distance is the distance between the two buses. Okay, example 4. A tourist at Cape Spear sees a container ship at an angle of depression of 23 degrees and a sailboat at an angle of depression of 9 degrees. So this would be your line of sight, your horizontal, from where you are taking these measurements. So you'd measure down from that horizontal. So the first one is a container ship would be 23. So this angle here to the container ship would be 23 degrees. And then to the sailboat would be 9 degrees. And then it says the tourist is 33.5, so we'll put 33.5 meters above the water. So that would be this distance from here to here. It says how far apart are the two vessels, so we're looking for this again. So again, we have a smaller right triangle from here to here to the container ship back here. And then we have an outside right triangle which goes from here to the sailboat, back to this point here. So if we could find this length of this side here in the big right triangle, we'll call that W, and then subtract this length right here in the smaller right triangle, we will get, again, we will get X, very similar to the last question we just did. So if we call, I'll just put letters on this again just to make it a little bit easier, A, B, C, and D. So in triangle, it doesn't matter which one you start with first. In triangle ABC, now we don't have, in triangle ABC, we don't have any angle measures apart from the 90-degree angle measure indicated in there, but we can use the angles of depression and parallel lines again. If this line is parallel to this, to the water, then this here, if this is 9, you have got the corners of the Z in parallel lines, that would also have to be 9 because they'd be alternate interior angles. And similarly, if this is 23 here and you've got parallel lines here and here, this would be alternate interior angle as well, so that would be 23. So in triangle ABC, I can use again the tan ratio, tan of 9 degrees, using the outside big triangle. The opposite side would be the 33.5, over the adjacent side would be W in the large triangle. And then I would cross multiply and get W tan 9 equals 33.5. So if you want to get W by itself, you need to divide both sides by tan 9. So that would be 33.5 divided by the tan of 9 degrees, which equals 211.5106, so I'm just going to round it off to 0.5. And then if we go up here and we go to triangle, the smaller triangle, triangle B, DC, it doesn't look like triangle, try that again, triangle B, DC, we have tan of 23 degrees is opposite, which is 33.5, over adjacent, which is Y. So then again, cross multiply, and we get Y tan 23 equals 33.5. So Y would equal 33.5 divided by tan of 23, which would give you 78.9 0.92105 around there, so that rounded up to 1 decimal place would be 78.9. So therefore x would equal 211.5 minus 78.9. Which is 132.6 meters. So the distance between the sailboat and the container ship will be 132.6 meters. Next example has two buildings separated by an alley. Joan is looking out of a window 55 feet above the ground in one building. She estimates that the measurement of the angle of depression to the base of the second building is 18 and the angle of elevation to the top to be 33. So Joan must be right here, and she's looking down at an angle of depression here to be 18. And this one here, her elevation angle would be 33, measuring up from the horizontal line of sight. So it says, how tall is the second building? So all we know is that this distance here from the ground up to where Joan is 55 meters from here to here. So if this is 18 right here, using parallel lines again, I can assume that this is 18. Or, rather than that actually, I can use the 18, I can just basically not even have to worry about that, I can just use 55. If this is 55, then this is 55. And then I'm inside the triangle because I want to find this distance here and this distance here and add them to get the full height of that second building. So if this is 55, then I know that I want to, basically what I want to find is this right here, because I know up to here is 55 and I want to add this on to get the height of the building. So I don't have enough information in the top triangle, right triangle. I have to use the bottom right triangle, and it would make sense to find this piece right here because that is a side in the other triangle that I want to use. So that's what I'm going to do first. I'm going to find W, and again I would have to use tan of 18 degrees would be opposite, which is 55, over adjacent, which is W. And then I would cross multiply. And to get W by itself, I need to divide both sides by tan 18, so it disappears on the left side and shows up on the right side when I divide it out of both sides. And that gives me 55 divided by tan 18 gives me 169 point, it's 0.2725 on the calculator, so I'm going to round it off to 0.3, and that would be meters. And then I want to take that W and use it in the other right triangle, top right triangle, from where Joan is looking to the top of the building, down, and right here. So I'm on this right triangle now, and I would use tan of 33 this time, and it would equal the x that I want over the adjacent, because opposite would be x, and adjacent would be the W that I just found, which is 169.3. So then I cross multiply. And I get x equals 169.3 times the tan of 33. I'm going to put that in the calculator. That gives me 109.9447. So if I round it off to 1 decimal place, that would be 109.9 meters. So therefore, the height of the building height of the second height of the second building would be the 55 meters plus the 109.9 meters, which would be, oh, it's 164.9. 164.9 meters. Okay, these next couple of examples have to do with three-dimensional objects, and we're going to be using a rectangular prism, and we're asked to find the length of the body diagonal, which goes kind of through the inside from opposite vertices from H to B. In this particular example, the body diagonal goes from H to B, and it will be the diagonal that cuts through the inside of the prism. It is a section that we sometimes leave out because we just don't have the time to fit it in the course, and more than likely we'll probably have to leave this out in class, but I'll just go through the examples just in case you want to try them, or if we do get it done. All right, so the first one there, you have to determine the length of the body diagonal from H to B, and if you look at the triangle that contains that body diagonal, the triangle that's shaded in blue there, going from H to B to F, that we don't know any of the side lengths besides this one right here. We know would have to be 8 meters because it would have to match what G to C is. Okay, but this one we'd still need another side length or an angle or something to be able to figure out what the body diagonal is. So if we look at the triangle created by points, the vertices H to F to G, we notice that there would be a right angle in this triangle, and it's hard to see with 3D pictures sometimes, but if you think about the bottom of this rectangular prism, F to G to H would actually be your right angle there. And again, it's hard to see that because right now the way it's drawn two-dimensionally, it doesn't look like it's a right angle, but like that would be in a corner. So it would have to be the right angle. So that would make HF your hypotenuse of that right triangle, and then GF and HG, right here and right here, would be the legs of that right triangle. So we know that 7 is given to us for GH, and we know that FG should be the same as EH, right here. So that would mean this would have to be 5 meters. So that means that HF squared then, the one we're looking for, would equal, if we look down here, HF squared would equal 5 squared plus 7 squared using the Pythagorean theorem. So then HF squared is 25 plus 49, HF squared is 74, which means HF is the square root of 74. So that there would be the square root of 74. And then we can now go back to the triangle that had the body diagonal. So H, if you look back at our diagram, H to B to F. So H to B to F, we know that HF, we can fill in as root 74. We already know that FB is 8. So then again, we can use Pythagorean theorem to find out what HB would be the body diagonal. So BH squared would be the root of 74 squared plus 8 squared. And that would mean that BH squared would be 74, because the square root of 74 times itself will give you 74. And then 8 squared is 64. If we add those together we get 138. So BH would be the square root of 138, or approximately 11.7. So the next question asks us to find, if we go back, the measure of angle BHF, which is this angle right here. This angle right here in our blue shaded triangle there in the inside, in the interior of the rectangular prism. So we're looking for that angle. Now we have the sides, we just found the sides of HF to be root 74, and we know the side BF is 8, so all we have to do to find that angle now is look at the information we have in reference to that angle, we have the opposite and the adjacent, so we would use tan. And tan of opposite over adjacent would be tan of 8 over root 74, which if we use our calculators and go inverse tan of the angle, inverse tan of 8 over root 74, we get 42.9 degrees, or approximately 43 degrees. Okay, in this example we have to determine the shortest distance from A to B. So that would be this shortest distance would be the straight line distance from A to B. So it would be basically a diagonal across the bottom of that rectangular prism. So I'm just going to put an X there because that's what we're looking for. And if you look at this figure, that X would be the hypotenuse of the right triangle formed from B to this vertex right here to A. So I'm going to put C on this vertex, and I'm eventually going to need this one up here too, so I'm going to put D there. So if I look at the triangle ACB, that is a right triangle because there's going to be a right angle. It's the corner of that. If you think of that, visualize that as the bottom of the rectangular prism. There's going to be a right angle created from BC and CA intersecting. So if I want to find that, I don't really have any information in that particular triangle, but if I could find this side right here and this side right here, I could use Pythagorean theorem then to find x. And I can find w and y if I concentrate on using triangle ADC first. That would be this triangle right here. It would have A, right angle right here, and D right here, and C right here. And we know this is what we'll be looking for, A to C. And we do know we're given that this is a 48-degree angle, and we're given that this is 12. Because that would be like the side, outside of that rectangular prism. So we know those dimensions there for that triangle. So we could use, if we look at the angle of 48, in reference to that angle we have the adjacent and the hypotenuse is 12. So that would mean we would use the cosine of 48 is adjacent, which is y, over 12 hypotenuse. And then we would cross multiply that and get y equals 12 cos 48 degrees, which would be 8.029, so on. So if you round it to one decimal place, it would be 8.0 centimeters. Then if we move to triangle BCD, we have this kind of a diagram where the right angle would be here, B, C, D, and we know that this is 18, and we know that this is 37. So this would be the front face of that rectangular prism. And we would know that the cosine, again, it would be cosine we're looking for because BC is what we're looking for, and that's the adjacent side in reference to the angle of 37. And the hypotenuse is 18, so we would be using cosine again of 37 is adjacent over hypotenuse. And then we would cross multiply to get W equals 18 cos 37. And that gives us 14.375, so on. So if you round that to one decimal place, it would be 14.4 centimeters. So then if we move over here to get some space, then we know that using the Pythagorean theorem, we know that we've got a right triangle ABC. So the right triangle ABC would have w squared plus y squared equals the hypotenuse, in this case would be x squared in that right triangle. So if we fill those in, we've got 14.4 squared plus 8.0 squared equals x squared. So if we work those out, we've got 207.36 plus 64, and that's going to give us x squared equals 271.36, and so x would be the square root of 271.36, which would mean that x would be approximately 16.473, so on. So x is approximately 16.5 centimeters. So I'm just going to organize this a little bit because this was my first step, this was my second step, and then this was what I did last. Okay, so the next example asks you for the measure of angle CAP, which is the angle between the body diagonal and the diagonal of the base of the square prism. And again, you don't have all the information you need in that right triangle, and that right triangle PCA would have a right angle right here. But we again don't have enough information in that triangle, so we're going to have to take something from one of the other triangles that has something that we can use in the triangle we want to use. So I'm going to look at this one down here, C to D to A. This would be a right angle right here. So if I look at triangle CDA, I have 5 squared plus 5 squared, because those would be the legs of the right triangle, should equal x squared, would be the hypotenuse. So then that would give you 25 plus 25, or x squared would equal 50. And x would be the square root of 50, which would mean, I'm going to move that up a little higher in case I need the space, which would mean that x would equal 7.071, so on. So that rounds off to be about 7.1 centimeters. And then I can use the right triangle, triangle PCA. I have basically, I have that this is 5, I have that this is 7.1, this is P, this is C, this is A, and I'm looking for this angle in here. So if I'm looking for that, I can use, again, in terms of the angle I have the opposite and I have the adjacent. So that would be the tan ratio. Tan of the angle is opposite over adjacent. So the angle would be inverse tan of 5 over 7.1, which would be 35.154, so on. So if we round that off to the nearest degree, that would be 35 degrees. Okay, and that's the end of that section. There's some questions there on pages 118 to 121 of your textbook that you can try to practice the material in this section.